Warm welcome, everyone. AICTE sponsored scheme for preparing SCSC students for higher education, yet coaching, Prerana scheme by Erode Sengunthar Engineering College, Tamil Nadu. Now we are going to discuss about the topic of overview in digital logic circuits. It was going to handled by myself, R.Senthilkumar, Assistant Professor, Department of Electrical and Electronics Engineering, Erode Sengunthar Engineering College, Erode District, Tamil Nadu. Okay. In digital logic circuits, first of all, we are uh, discuss about the overview of DLC, digital logic circuits. The first topic of is binary logic and gates. Next, Boolean algebra. Next, standard and canonical forms. Next, K maps, simplification of K maps, and K max magnification. Next, about different types of logic gates. First, binary logic. What is meant by binary logic? Binary logic deals with the binary variables. Binary variables such as zeros and one. Only two discrete values with logic operations is known as binary logic. Okay. There are three basic logic operations, binary logic operations such as AND gate, OR gate, NOT gate. What basic operations AND or AND not. Binary variables are logic variables. Both are same term are typically represented as letters A, comma B, comma C, M and OP, X, Y, Z, such like that. Okay. Binary logic functions. Function of some variables is equal to expression. For example, f of x comma y comma z is equal to x bar into y into uh, z plus x y z bar, like that. So function of variables is equal to expression. Variables such as set of binary variables. Okay. If we have three variables, we have three different denotation letters x, y, z, or a, comma b, comma c, like that. Expression in expression consists of operators, variables, constants, or groupings. Operators such as addition, sum, or product, or complement or uncomplement. Basic logic operations. Next slide. Basic logic or binary operators are AND operator, NOR, OR operator, and NOT operator. In that, AND and OR are called as binary operators. NOT is mentioned as unary operator because it is single complementer. Okay. Now, function of a comma b is equal to a into b. Okay. It is AND operation. F is one function f of a comma b is equal to 1 if and only if a and b both are equal to 1. If any of one value is a is 0, then the result is 0. Okay. 0 into 1 is 0, 1 into 0 is equal to 0, or 1 into 1 is equal to 1, 0 into 0 is equal to 0. If both values are high, then the output is 1. Okay, this is called AND operation. G of a comma b is equal to a plus b. G is high, high means 1, 0 means low. Okay. G is high if either a equal to 1 or b equal to 1. Any one input is, at least any one input is high, the output is high. This is called AND operation. Sorry, OR operation. Or for AND operation, two variables are producted. For OR operation, two variables are added. If any one of input is high, then the output is high. Okay. Next, h of a is equal to a bar. This is not operation. If the output is complement of input. If h is equal to 1, then the output is, sorry, if h is equal to 1, if input a is 0, if h is 0, if input a is 1. Okay, if input a is low, the output h is high. If input a is high, the output h is low. This is normal not operation. This is the basic logic operations. Okay, so digital logic circuits is the 20 percentage of gate questions are asked from digital logic circuits. Basic logic operations. One bit and resembles binary multiplication. For example, 0 into 0 is equal to 0. 1 into 0 is equal to 0. 0 into 1 is also equal to 0. Anything multiplied by 0, the output is 0. Okay, 1 into 1 is equal to 1. This is basic binary multiplication. 1 bit and resembles 1 bit logic and. Next, 1 bit logic R resembles addition operation. Okay, 1 bit logic R resembles binary addition except for one operation. Now, 0 plus 0 is equal to 0, 1 plus 0 is equal to 0, or 0 plus 1 is equal to 0. 1 plus 1 equal to 1 for 1 bit binary addition. For normal binary addition, 1 plus 1 is equal to 10. Okay, what is mean by truth table? What is a truth table for logic operators? Truth table, it is the tabular form that uniquely represents the relationship between the input variables of a function and its output. Okay, truth table is nothing but relationship between the input variables of a function and its output. Okay, it is called truth table. Nothing but relationship between the input and output functions. Okay, okay, two input and gate. Okay, the two input, a is one input and b is another input. Now the output f is equal to a into b. And operation means both inputs are multiplied, that is product. The or operation means sum, both inputs are added. Not operation means complement, output is complement of input. Okay, for two input and gate, like that we have one coin. Coin has both sides, head and another side is tail. Okay, if we toss the coil, one times we get the probability such as head, comma, tail, or tail, comma, head. First we had head, second time we have got tail. Okay, for single coin. For two coins tossed, we have guess the probability of tail, comma, tail, or head, comma, head, or head, comma, tail, or tail, comma, head. We have four combinations for two coins. For single coin, if we have tossed, we obtain one head or next time tail. Okay, if you have two coins tossed, we obtain tail, comma, tail, or head, comma, head, or head, comma, tail, or tail, comma, head. If you have two coins in the sense, so four possible combinations of output is possible in two input. Okay, if a and b are two input, then the output f is equal to a into b. So 0 into 0 is equal to 0, 0 into 1 is equal to 0, 1 into 0 is equal to 0, 1 into 1 is equal to 1. The output f is high, only both inputs are high in AND gate. For OR gate, a, b, f is equal to a plus b. Okay, 0 plus 0 is equal to 0, 0 plus 1 is equal to 0, 1 plus 0 is equal to also, no, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to also 1, 1 plus 1 is equal to 1. If any one of the output, at least any one of the output is, or at least any one of the input is high, the output is also high. Okay, so 0 plus 1 is equal to high, 1 plus 0 is equal to high, high plus high is equal to high. Okay, next NOT gate. Okay, output f is equal to input a bar. Okay, a is the input, f is the output. So input a 0, then the output is 1. Input a is 1, then the output is 0. Okay, okay, one question. Let a function f depend on n variables. How many rows are there in truth table of f? As I have already stated in previous slide, if we have one variable, we have the possible of, so if we have one coin, we have the possible of tossing one time is head and another time maybe tail, or tail comma head. Okay, so if we have one coin, that's the probability of two combination. One is head and another is tail. If we have two coins are the simultaneously tossed, we have got head comma head, or tail, or head comma tail, or tail comma head. We have four combinations. So the answer is 2 power n rows. Since if the input is 2, then 2 power 2 is 4. Okay, 4 possible combinations. Suppose if the input is 1, that is one variable, then the output possible combination is 2 power 1 is equal to 2. If the input is 0, then 2 power 0 is equal to 1. Okay, suppose if the input is 3, then 2 power 3 is equal to 8 possible combinations. So if we have 3 coins simultaneously tossed, then we have 8 possible combinations. Okay, this is the answer. So let a function f depends on n variables. How many rows are there in truth table? So see the previous slide. If we are having two input variables in AND gate, so the possible rows are 4. We are having two input variables in OR gate, so therefore the possible rows are 4. So see the not gate truth table. We have only one input A. Okay, therefore 2 power 1 is equal to 2. Therefore 2 rows are possible rows combinations. Okay. Next, what is mean by logic gates? Logic gates are abstractions of electronic circuit components. Okay, that operates on one or more input signals to produce an output signal. Okay, based on the logic gate operation, it produces an output signal. Okay, by one or more than one input signals. Okay. Okay, so now see two input AND gate, two input OR gate, two NOT gate. So NOT gate is also called as inverter. Why? Because of it is the complement of input. Okay, okay. AND gate F is equal to A into B. For OR gate F is G is equal to A plus B. For NOT gate H is equal to A bar. So A does means A bar. Okay. Next, timing diagram. See, different instant different inputs are on. So we are having two inputs, A, B. Okay, so A is initially high at T0 and low at T1, all still up to T3. Okay, again high at T3, still high up to T6. Okay, now see the second input B, it's low at T0 and high at T2. So this when the values say state the state change from 1 to 0 or 0 to 1 is known as transition. Okay, so transition defines the state changing from high to low or low to high. Some transition. Okay, it's called transitions. Okay. Here we assume propagation delay is 0. Okay, instantly all the gates are turning on. Now see if for AND gate for AND operation, F is equal to A into B. See the previous slide, F is equal to A into B, two input AND gate. So F is equal to A into B. See the A input is initially high, B input is 0. So 1 into 0 is 0. Now at T1, both inputs are low, so the output is also low. At T3, B is high, but A is low. Okay, so high 0 into 1, 0. So the output is also low. At T3, C, A input is high and also B input is high. So therefore 1 into 1 is 1. At T4, okay, one of the input is low. So therefore the output is low up to T6. Okay. Next output G is equal to A plus B. See the previous slide for OR gate G is equal to A plus B. So we have to if any one of the input is high, the output is high. This is the concept of OR operation. So see at T naught A is high, B is low, so therefore output is high. At T1 to T2 interval, all the inputs are low, so the output is also low. Okay, this is the OR operation. Next is NOT gate. NOT gate H is equal to A bar. So it is opposite to the input A. Okay. So at initially T naught, A is high. Therefore H is equal to A bar, so it is low. is a complement of input A. Next, what is mean combination logic circuit from logic function? Okay, consider function f is equal to, is an example one. Okay, consider function f is equal to a bar plus b into c bar plus a bar into b bar. Okay, define combination logic circuit, that is CLC, from logic functions. Okay, combination logic circuit can be constructed to implement a function f by appropriately connecting input signals and logic gates. Okay, we can obtain the combination logic circuit output by connecting the input signals and logic gates depends upon our desired function. Okay, so circuit input signals from input variables A, B, C. Okay, circuit output signals we obtain from function output capital F. Okay, next logic gates from logic operations. Okay, we obtain the logic operations from logic gates. Now, the F is equal to A bar plus B into C bar plus A bar into B bar is the combination logic circuit function. Okay, now see the logic circuit. Okay, depends upon the given considered function, the logic circuit is designed. Okay, now f is equal to a bar plus b into c bar plus a bar into b bar. So here see, we need one 3 input OR gate, two 2 input AND gate, and three we need 3 NOT gate, and the wires are also more. Okay, the connections are complicated. This is the combination logic circuit. We can minimize this combination logic circuit with different techniques. Okay, in order to design a cost effective and efficient circuit, we need to minimize the circuit size by also area, and also by reducing the logic gates we can also reduce the propagation time delay also. So propagation time delay is time required for the input signal change to be observed at the output line. Okay, application of output, sorry, output is the time interval between the uh, application of input signal and producer of output signal. Okay. Next step. Observe the truth table of f is equal to a bar plus b into c bar plus a bar into b bar. Okay. Next. And g is equal to a bar plus b bar into c bar. Here you see the truth tables for f and g by given input function a, b, c. So a, b, c is the 3 input variable. So therefore 2 power 3 is equal to 8 possible combinations are possible. Okay, 0, 0, 0, 0, 0, 1 by succeeding 1 up to triple 1. Okay, so for f and g are having the same values in truth table, but the different boolean expression we are having. Okay, truth tables for f and g are identical, that is same function. Use g to implement the logic circuit, that is less components. So by simplifying the boolean expression, we get g is equal to a bar plus b into c bar. Okay, here you see g is equal to a bar plus b into c bar. Now see the first circuit diagram. It is the previous circuit. First we design from f is equal to a bar plus b into c bar plus a bar plus a bar into b bar. Uh, this is the logic circuit. Here see f is equal to f function logic circuit diagram in first circuit. Second image shows that g is equal to uh, g value of Boolean expression. So here you see for first circuit we need one sorry, 3 NOT gate, 2 AND gate, and 1 OR gate. In the second circuit it resembles, it reduces one NOT gate and also one AND gate, and it reduces the propagation delay, area, cost also. Okay, in simple one circuit expression, one Boolean expression, we have reduced two components and also the size and the cost. So by simplifying the Boolean expression, we can reduce the cost, also area and size. Okay, next one is Boolean algebra. Very nice machinery used to manipulate in the sense simplify Boolean functions. So George Boole in the year from 1815 to 1864, his investigation of laws of thought. Okay, terminologies in Boolean algebra is literal, product term, sum term. What is meant by literal? It is a variable. A single variable is defined as literal or its complement. Okay, product term. Literals connected by product is called product term. It is connected by dot. It's called product. Literals connected by sum plus is called uh, a sum term. Okay. Boolean algebra properties. Let x be the Boolean variable. 0, 1 are constants. Okay. Now you see x is the Boolean variable in the sense. So it may be 0 or 1. Okay. X plus 0 is equal to x. Okay. X is the high value in the sense. So x plus 0 is equal to x. So x into 1 is also equal to x. Okay, now x plus 1 is equal to 1. See, if x is 0 is added with a high value, then output is always high. Okay, suppose if x is equal to 1 or either maybe 1 or 0. But the output is added with high value, so therefore, sorry, if x is the Boolean variable is added with a high value, then the output is also uniformly high value. Okay, suppose if x may be 0, so 0 plus 1 is equal to 1. So suppose if x is equal to high 1, so therefore 1 plus 1 is also equal to 1. Okay, so x into 0, okay, well, anything multiplied by 0 is equal to 0. Next, x plus x is equal to x. X into x is also equal to x. So 0 into 0 is equal to 0. So 1 into 1 is equal to 1. Okay, so 1 plus 1 is equal to 1 or 0 plus 0 is equal to 0. That is the x plus x equal to x or x into x equal to x. Now x plus x bar equal to 1. Suppose if x is equal to 0, x bar equal to 1, then 0 plus 1 equal to 1. If x is 0, x bar is 1, then output is 0. Okay, x bar whole bar. Okay, if x is 0, then x bar is 1. Again the x bar is bar. So now again the answer is in question, first question, 0. So this is called involution. So x double bar is equal to x. Okay. Okay. So now the next concept is duality. The dual of an expression is obtained by exchanging dot and plus. That is exchanging product and sum and 1 and 0 in it, provided the precedence of operation is not changed. Okay, the dual of an expression is obtained by exchanging product and sum and zeros and 1. Okay, wow. Cannot exchange x with x bar. Okay, now let's see the example. Find h of x comma y comma z. The dual of f of x comma y comma z is equal to x bar y e z bar plus x bar y bar z. So, so for duality, we can it's obtained by exchanging product with multiplying, product with addition. So see, x bar into y bar into z bar is converted as x bar plus y plus z bar. Okay, now the sum is converted into dot. Now x bar plus y bar plus z is another term. This is the duality. Okay. With respect to duality, identity 1 to 8 have the following relationships. Okay. So x plus 0 is equal to x. We know that x into 1 is equal to x. Dual of 1. So here is the dot. Addition is such a exchange into dot and 0 is exchanged into 1. Okay. So x plus 1 is equal to 1. Now x into 0 is equal to 0. Here the addition is exchanged into subtract and 1 is exchanged into 0. So like that we have obtained the dual. lesson 6. Okay, next x plus commutative law. Okay, x plus y is equal to y plus x. This is commutative law. Okay, next x into y is equal to y into x. Okay, 1 into 1 is equal to 1 into 1. 0 into 1 is equal to 1 into 0. Like that. Next is associative law. X plus second term is x plus second term is y plus z is converted into x plus y first term, then plus z is second. This is commutative law. This also for product x into y into z is equal to x into y into z. This is associative law. Next one, distributive law. Okay, x into term y plus z is equal to multiplication. So x into y plus x into z. Okay, next question, x plus y into z. So x plus y into x plus z. This is distributive law. Okay, next question is x plus y whole bar is break into x bar into y bar. Suppose if x into y whole bar is transferred as x bar plus y bar. This is called as De Morgan's theorem or De Morgan's law. Okay. Okay. Absorption property. Okay, see in first example x plus x into y is considered as x. Okay, wow. Second question, see x into x plus y sequence is also equal to x. This is dual principle. Okay, so if we see the proof x plus x into y is equal to, see x, we can write the first term x as x into 1. X into 1 is also same answer x, plus second term x is x into y, just written it. So in first term and second term, see x is common. So we take x as common. Now we see 1 plus y is the second term. Okay, x into 1 plus y. Therefore, y plus 1 is also written as 1. Okay, any boolean variable is added with high value, the our result answer is high. So x plus 1 is equal to 1. So like that, y plus 1 is equal to 1. So therefore, x into 1 is equal to x. This is hence proof. Okay, hence proof. Okay. Next, this is the power of duality. Okay, you can check the power of duality. Okay, truth table. Truth table enumerates all possible combinations of variable values and the corresponding function value. Okay, normally the truth table consists of, or truth table comprises input variables and output function variables. So input variables, here you see the three variable input x, y, z. So for three input variables, we have 8 possible combinations. Check. 2 power 3 is equal to 8. Okay, so we are having 3 possible, sorry, 8 possible combinations of 0 0 0. We add a succeeding one. Okay, 0 0 1 0 0 0 1 0 0 1 1 100 101 110 111, like that up to triple one for 3 input. So for 4 input, we up to 4 1 we are having 16 possible combinations. 2 power 4 is equal to 16. Okay. Okay, so now see the function f of f1 of x comma y comma z, f2 of x comma y comma z, f3 of x comma y comma z. Okay, also on to write for different function values. Okay, truth table is a unique representation of Boolean function. Truth table is just Boolean, the unique representation of the Boolean function. If two functions having identical truth tables, the functions are equivalent. Okay, truth table can be used to prove equality theorems. However, the size of the truth table grows exponentially with the number of variables involved, hence unwieldly. Okay, this motivates the use of Boolean algebra. So now see, if we are having two input, we are having four possible combinations. So if we are having three input, we are having 8 possible combinations. Now we see if you are having four input variables, now the possible combinations is 16 rows. If you now think if you are having 5 input variables, then the possible uh, output combinations are 32, like that. Okay. Okay. See, Boolean expressions is unique or not if we are having both functions as same. Now check f of x comma y comma z is equal to x bar y bar z bar plus x bar into y bar into z bar plus xy z bar. Okay. Now see, now take last two term. Uh, check x bar y into z bar plus x y into z bar. Take y and z as common. Now in the bracket x plus x bar is considered as 1. Therefore g of x comma y comma z is equal to some expression. See here both both Fourier functions are not unique. Okay, not same. But see the truth table. 1 1 0 0 1 1 0 0 0 0 0 0 1 1 0 0. So this here the corresponding truth tables for f of and g of are to the right. So they are identical. If they are identical, the Boolean expressions are equal. So thus f of function f is equal to g function g. Next, algebraic manipulation. So this algebraic manipulation is the one and best simplifying digital circuits, a useful tool for simplifying the digital circuits. This algebraic manipulation only reduces the cost size of the circuit and make the circuit to work faster by reducing the propagation delay because of reducing the components used in the circuit. Okay, why do it simpler? It's simpler. Algebraic manipulation simpler can mean cheaper, smaller, and faster. For example, simply f is equal to x bar y z plus x bar y z bar plus x z. Now here see, for if I see the first two terms, take x bar and y as common. Take z plus z bar plus xz. So z plus z bar is having the formula z plus z bar is equal to 1. So therefore, x bar into y plus xz. Okay. So here is you for in check simplifying f is equal to x bar y z bar. Here we are into 3 input and get 3 and get 3 input and get 1, 2 3 input and get 2, 2 OR gate are needed. Here we need just 2 and get 1 OR gate. Okay. So here for up to 4 to 5 logic gets reduced. This makes the propagation delay less, cheaper in circuit, cost is low, size of the circuit is decreased. Okay, so algebraic manipulation. Prove x bar y into z plus x bar y z plus x y z bar is equal to x into z bar plus y into z bar. Okay. Next, complement of a function. The complement of a function is derived by interchanging product and sum and 1 and 0 and complementing each variable. Otherwise, interchange ones to zeros in the truth table column showing f. Okay, this is the complement of a function. So the complement of function is not the same as dual of a function. Both are different. Okay. Okay. So see example. Find g of x comma y comma z. The complement of f of x comma y comma z is equal to x y bar z bar plus x bar y z. Now see g is equal to f complement. Okay. Find g complement of f. So g is equal to f complement. Okay. That is g is equal to f bar is equal to by taking the whole given value as bar. Okay, so x into y bar into z bar plus x bar y z whole bar. Okay, now see by breaking the bar, that is De Morgan's theorem by a De Morgan's law. Okay, x we can change the product as sum and sum as product. Okay, before that we have by before that we divide the whole bar. Okay, so x y bar z bar whole bar into x bar y z whole bar. Now again the De Morgan's theorem. So x bar plus y bar, oh sorry, x plus y, x bar plus y plus z into x bar plus y x plus y bar plus z bar. This is De Morgan's. So the complement of a function can also be derived by finding the function's dual and then complementing all of literals. Okay, next one is canonical and standard form. Okay, no canonical standard forms are equal. Now see, we need to consider formal techniques for the simplification of Boolean functions. Identical functions will have exactly the same canonical form. Okay, identical functions will have exactly the same canonical form. Okay, it consists of min terms and max terms. So min terms as sum of product and max term as product of sum. So sum of min term such as sum product of max terms. So sum of product is considered as SOP and product of sum is considered as POS. Okay, definitions. In min terms, max terms, the terms, literals. A word here, literal a word is a term, a variable or its complement is termed as literal. Next one is product term. What literals connected by product is called product term. Literals connected by addition. This sum is called sum term. Min term is defined as a product term in which all the variables appear exactly once, either complemented or uncomplemented. Okay, wow. A product term in which all the variables appear exactly once. Okay. Max term is some term in which all the variables appear exactly once. So in min term and max term is nothing. Min term is nothing but product term. Max term is nothing but sum term. Okay. Either complemented or uncomplemented. But all the variables are appeared. Okay, min term. Min term represents exactly one combination in the truth table. Okay, this the max term. It represents exactly one combination in the truth table. Both are same. Min term is denoted by mj and max term is denoted by capital MJ. Okay, see the both. Okay, decimal equivalent of where j is the decimal equivalent of min terms corresponding binary combination. Here also where j is the decimal equivalent of max term corresponding binary combination. Okay, wow. Okay, a variable in mj is complemented if it is value in bj is 0. Okay, the value in decimal equivalent of bj is 0, the mj is complemented, otherwise is uncomplemented. See in max term, a variable capital mj is complemented if in its value in bj is 1, otherwise it is uncomplemented. Okay, okay. So in term, see example, assume g variables a, b, c and j is equal to 3. That is 3 variable. Okay, then bj is equal to 0, 1, 1. Okay, and this corresponding min term is denoted by a bar bc. Okay, a bar bc. So a bar term is source 0, bc source 1, 1. So 0, 1, 1. So a bar bc. This is min term. See the max term example. Assume 3 values a, b, c and j is equal to 3. Then bj is equal to 0, 1, 1. Then corresponding max term is denoted by 0 is considered as a, 1 is considered as b bar, c is considered as, so 1 is again 1 is considered in t term is considered c bar. So it is product sum of sum, not sum of product. So a plus b bar plus c bar. See the difference of both min term and max term. So min term a bar bc, so max term a plus b bar plus c bar. Okay, wow. So mj is min term mj is complemented if the value in bj is 0. Value in bj is 0, the mj is complemented. In max term, the mj is complemented if value in bj is 1. So in binary value, when the value is 1, it is the mj is complemented. Otherwise, it is uncomplemented. Okay. So here the truth table notations for min term and max term in say one single table. So min term and max term are easy to denote using a truth table. Okay, assume three variables input x, y, z. So for the x, y is 0, 0, 0 up to 1, 1, 1, 4. See the min term 0 for 0 it shows x bar. For y it shows sorry y input variable 0 it shows y bar. For z input variable 0 it shows z bar. So this is equal to m naught, that is m0, this zeroth value. Okay, zeroth row. So M0. So small m denotes min term. In max term, it denotes capital M0. So Mj value is equal to 0. Now see, uh, when input x, y, z is 0, the max term is uncomplemented. That is uncomplemented. So x plus y plus z. So this here the max term is product term. Sorry, sum term. So x plus y plus z. Like that. Both minterm and max term are opposite to each other. Okay, canonical forms consists of canonical sum of product and canonical product of sum. Canonical sum of product. The minterm included are those mj such that f is equal to 1 in row j of the truth table. Max term included are those mj such that f is equal to 0 row of truth table. So here see the truth table A, B, C for different values up to 111. Function F1 0 1 1 0 1 0 1 0. Okay, here you see when the output function F1 is 0, it is termed as sum of product of sum. When the output F1 value is 1, that values are max term values. Okay, min term values are the min term values are 1 value, the max term values are 0. Okay, so f1 of a comma b comma c equal to, see here take the 0 values, m capital M naught, capital M4, M3, capital M5, capital M7. Okay, so the max term values are product term, so M1, M naught into M3 into M5 into M7. uh, See the minterm values m1, m2, m4, m6 are minterm values, so it is sum of product. So m1 plus m2 plus like that means you have to write. Observe that mi, that is minterm, is equal to max term mj bar. Both are complementary to each other. Okay, shorthand. Next, min terms are represented by summation symbol and max terms are represented by pi symbol. Here you see f1 of a comma b comma c is equal to summation m of 1 to 4 6. So in this function indicates where summation indicates that this is a sum of product form. Okay, please remember in mind summation m indicates min term. Okay, so this is sum of product. Minterm means sum of product. And m of, again you have to write minterm of 1 to 4 6 indicates that minterm to be included are, which minterms are included are m1, m2, m4 and m6 minterms are included, which indicates that. Okay, simply. Next, f1 of a comma b comma c is equal to phi of m of 0 3 5 7 if the given value is like that, where phi indicates that this is the product of sums form, and capital M of 0357 indicates that max terms to be included are M0, M3, M5 and M7. Okay, since Mi is equal to capital Mj bar for any j, summation m of 1246 is equal to phi m of 0357 is equal to f1 of a comma b comma c. So minterm is complement to max term. Next, conversion between canonical forms. Okay, now you see replace summation with phi or vice versa. Okay, give an example. F1 of a comma b comma c is equal to the given expression a bar b bar c plus a bar b c bar plus a b bar c bar plus a b c. So which are the minterms m1, m2, m4, mc. Suppose if you have to convert into standard max term, okay, summation 1 to 4 6 is minterm values. Suppose you have to convert into max term, you put phi of for 1 you put 0, 2 you put 3, for 4 you put 5, for 6 you put 7. Then you have write that a bar b bar c in minterm is written that a plus b plus c bar. Okay, then convert the product into sum and sum into product. Again, a bar, b, c bar, you have written that a plus b bar plus c, like that. Okay. Standard forms. This is POS, product of sum. Okay. Next, conversion of SOP form standard to canonical form. Okay, there are given questions may be some given expressions may be in standard form. We have to convert into canonical SOP form. Okay, uh, for for that expand non-canonical, that is standard terms, by inserting equivalent of one in each missing variable x. Okay, so by Boolean expression algebra, we know that x plus x bar is equal to 1, x into x bar is equal to 0. We know that terms. Okay, so we have to remove the duplicate midterms also. So suppose if the given expression f1 of a comma b comma c is equal to a bar b bar c plus b c bar plus a c bar. This is the given standard SOP form. In the sense we have to convert into canonical SOP form. So canonical SOP form means all the terms are having all the three. Suppose if the input f1 of a comma b comma c is three literal, three input variable means the result is also in uh, three output literals. So see, you see f1 of a comma b comma c is equal to a bar b bar c plus b c bar plus a c bar, in the sense. Now you see the first term a bar b bar c. So we are having three input variables. So in this term also we are having three output variables. Okay, so there is no problem, no missing literals in this first term. Now you just see the second term b bar b c bar. So here the missing literal is a. So you write that a plus a bar into bc bar. So a plus a bar is equal to 1 into bc bar. So no value is changes. So you write that. Say third term we have missing term as b. So you write b plus b bar into ac bar. Okay. Next, by using the De Morgan, distributive law or associative law, a bar b bar c. So you just multiply. Okay, a b c bar, next plus a bar b c bar. Again the next term a b c bar plus a b bar c bar. Okay, now you see the second term and fourth term are having same term or same terms. So you omit one term. Okay, now if we omit one term, in the sense we are having a final result obtained as four terms. This is the standard canonical form. Conversion of standard into canonical SOP form. For POS also we are having same method. Okay, there we are having x plus x bar. Here we are using x into x bar equal to 0, removing the duplicate max terms. Okay, uh, so here the given question is f1 of a comma b comma c is equal to f of a plus b plus c into b plus c bar into a bar plus c bar. This given expression is standard product of sum. Okay, product of sum, not sum of product. This is product of sum. That is max sum. Okay. Here you see in second term we are having the missing literal as A. In third term we are having the missing literal as B. So you just add A into A bar. In third term we are missing the literal B. So you just add B into B bar. Again using the multiplication method, we multiply the all the terms. Okay. Okay. Finally we omit the same repeated terms. This is the result. Okay, so next topic is K-map. K-map means Karnaugh maps. So K-maps are graphical representation of Boolean functions. Here in K-map, we are having different variables of K-map. So one map cell corresponds to a row in the truth table. One map cell corresponds to a row in the truth table. Okay, K-map is just a graphical representation of Boolean function. This K-map is used to solve the uh, Boolean functions. Also, one of cell corresponds to a minterm or maxterm in the Boolean expression. Multiple cell areas of the map correspond to standard terms. Okay, we are having different variables of K map. One variable K map, two variable K map. Okay, two variable K map, three variable K map. Again, we are having four variable K map. Okay, with the different examples. Five variable K maps also having, but this method is something difficult to solve. Okay, so the K map simplification of K map and its operation we will discuss in next uh, pre-RANA class. Okay, we will discuss in next pre-RANA class. This is something we need more time to solve. Another 1 hour is needed for this K map simplification method itself. So we will discuss in next class. We go for next topic as more logic gates. We are having three types of logic gates. One is basic gates, second one is uh, universal gates, and the third one is other gates. So the basic logic gates are basic binary operations gates. Okay, so AND gate, OR gate, and NOT gate are the basic logic gates. NAND gate and NOR gate are the second type of gate. It is universal gates. Okay. Uh, Third gate, the other gates are exclusive OR gate and exclusive NOR gate are other types of gates. Okay, so okay, more logic gates in AND gate. First, you see the symbol. Okay, AND gate symbol as like the big D. X is one input and Y is second input. X and Y. So X into Y. Okay. If X and Y both values are 0, the output is 0. If any one of the input is low, the output is also low. This is the AND gate operation. Next gate you see the symbol of OR gate. OR gate you see that like arc structure. XY. Uh, X and Y have two inputs, X or Y. That is X plus Y. 0 plus 0, 0. 0 plus 1, 1 plus 0, 1. 1 plus 1, 1. Okay. Like that, if any one input is high, only one input is high, the output is high. Third logic gate is NOT gate, basic gate. Okay. If input is X, the output is X bar. If input is bar, the output is X. Okay. Here the like triangle like symbol with the bubble. Bubble indicates the NOT operation. Additional logic gates are used for practical reasons. Next, NAND gate and NOR gate and buffer gate. Buffer is just a memory for storing a value. If the buffer is nothing but I see here X is input and F is output. F is equal to X. The X is 0, the F is also 0. If X is equal to 1, F is also 1. The buffer is a memory element, secondary memory element. Just storing the value. The gate. Okay. Next, NAND gate. So not plus AND gate is NAND gate. Okay. Here you see the AND gate output in previous slide. See the output 0 0 0 1. See NAND gate 1 1 1 0. So using the AND gate with the bubble is called NAND gate. Using the OR gate with the bubble is called NOR gate. See in OR gate output is 0 triple 1. See in NOR gate 1 triple 0. So likewise, NAND and NOR gates are opposite to AND and NOR gate. Okay, so AND plus NOT gate is NAND gate and OR plus NOT gate is NOR gate. NAND gate is universal, known as universal gate because any digital circuit can be implemented with NAND gates alone. Okay, to prove the above, it is sufficient to show AND and OR and NOT can be implemented by using NAND gates. NOR gate is also called as universal gates because any digital circuits can be implemented with NOR gates alone. Okay, this is the special special what you can say uh, special features of NAND and NOR gates. NOR gates, that is where it is a universal gate. So this is called as universal gates. So here see, you can see by using the NAND gate we can design the NOT gate in first circuit. See in first circuit, first symbol. Okay, the NAND gate with given input we can implement as NOT gate. Use next image second symbol you show, by using two NAND gates we can design the AND gate. See the third image, by using three NAND gates we can design the OR gate. So we can call the NAND gate as universal gate. Okay, and OR symbolically indicates that SOP, sum of product. By using and OR, now the final expression we got as x into y plus y into z. So it represents sum of product. Now you see NOR gate. NOR gate is also called as universal gate because any digital circuit can be implemented with NOR gates law. This can be simply proved as with NAND gates. Okay, so now you can see the NOR gate. First circuit you R plus NOT. Okay, that is called NOR gate. You can implement this as uses NOT gate, NOT plus, and you can use as okay. Next, other gates are called XOR and exclusive NOR. Okay, XOR gate is also called as not equal gate. Okay, just draw the R symbol gate with front side as arc before the after the input. Okay, XY arc and then like OR gate. It's called as XOR gate. XOR gate is also called as not equal gate. See the truth table. XOR gate is mentioned symbolically represented as plus exclusive plus with round is called exclusive. Okay, so X exclusive or Y, that is called XOR gate. See here the if the two input is if the two input is same, the output is low. If any one of the input is different, the output is high. This is the XOR gate exclusive. Okay, so now you see not equal gate. So if two inputs are not equal, then the output is high. Check. If two input 0 and 1 is not equal, therefore the output is high. 1 and 0 is not equal, therefore the output is high. Two inputs are equal, then the output is low. Next, the XNOR gate. XNOR gate is represented as equal gate. So in XOR gate, you just buffle, then you obtain this symbol as XNOR gate. So here you see, if the two inputs are equal, the output is high. Okay, if any one of the output is different, the output is low. So you see 0 plus 0 into 0 exclusive or y whole bar is 1. So the two inputs are 1 and 1 are equal, therefore the output is high. This is called XNOR gate. Okay, exclusive or operation. Okay, so thank you. From this class, we can know about the basic overviews of digital logic circuits. This is the basic overview only. In next class, we will discuss about the next topic, K maps, like that, counters, registers, flip flops, memory elements. Okay, half adder, full adder, like that. Okay. Thank you. Thank you all.